Okay, so what exactly do we just prove, right? So we proved the following. We proved that um we proved that for any irrational number, the limit of these two averages of the sum of the points and the translations is zero. So let's write that down. So we have right now, if theta is irrational, um, then the limit as n goes to infinity, 1 over big N of sum, little n go from 1 to big N of n theta. The average value of this fractional parts of integer multiples of theta and the average of the translation of these things by any t. So this is for any real t, like this. We'll get this to be 0. Okay, so this is what we have discovered so far. And as it turns out, this is pretty close to what we want. Okay, so let's see. I want to change this to maybe not as. Can I change it to be not as? Change the color. It's okay. All right. So I want to show that this is equivalent to uh, equidistribution. So how do we prove that, right? So let's show this is our new task. Let us show that um, for a sequence xn inside 0, 1, um, the quality of for every b between 0 and 1, the limit as n goes to infinity of 1 over n of the number of points lying less than and b is equal to b if and only if and only if for every real t, the limit as n goes to infinity of these differences of the averages n is 0. I want to show this equivalence. If we can show this equivalence, then we basically proved we proved equipartition, equidistribution. Okay, so these are characterizations of the same thing. So why is that true? Right. Question. Mm, well, where should we start? How should we start? Let's take a look at the differences, right? So let's notice a couple of things. Let's notice um, this inequality, or this rule. What is x minus y, right? The fractional part of this. Well, the fractional part of this is equal to a couple things. Well, this is equal to the fractional part of x minus the fractional part of y if the fractional part of x is bigger than or equal to the fractional part of y like that, or it's 1 plus the fractional part of x minus the fractional part of y if otherwise, like this. Okay. So, what can we do is that the summation of n go from 1 to n of xn plus t, let's say t is any real number here, can be thought as, use the subtraction to describe this. Like this. And now we have two cases. What are the two cases? Well, case one is when we have this one and then this one, right? So we're going to denote a couple things. So denote the set A to be the set of all integers less than big N, such that xn is, well, the fractional, well, xn itself is already, a sequence in 0, 1, so I don't need that part. So this is bigger than or equal to the fractional part of minus t. Okay, so let's call that A, and let's set B to be the complement of that. Like so. All right. So therefore, we see that the sum and go from 1 to n of xn plus t is equal to summation when n is a set A. When it's set A, then we have case A, then we'll just have xn minus um this, that, right? Plus the case of B, then we have 1 plus xn minus this, like so. All right, what's the big deal here? The big deal is that the xn terms they combine, that is still the sum of 1 to big N of xn. And we'll put the parentheses here like that. We also have subtracting this constant right here, like so, right? A mini, B mini, yeah. And then we're curiously plus the sum of n in B1, which is the size of B, right? So this is the size of B. So this is curious because this is not going to take the role of B. So what we see that is for any real t, comma, let's move some terms around. Um, the sum of n go from 1 to big N. Let's move this here, move that there, of xn. Let's divide by n as well, minus 1 over n. So I'm going to do this term, sum of n go from 1 to big N. So these are the difference in averages, like that, is equal to, right? So I move this over, which we divide by n, so that is gonna give us minus t minus the size of b. And the size of b is just the number of, and we divide by n as well. So 1 over n of number of terms. Let's write this down below. Like so. So indices such that xn is less than the fractional part of minus t. This is great. This is great. Why is this great? Because we can now let the role of b to be this term right here. So first of all, we know this is true for any real t. All right. So let's do it. Suppose, okay, let's call this. This is gonna be our fundamental lemma here. Okay. Suppose for any 0 less than b less than 1, we have the limit as n goes to infinity of 1 over big N, the number of terms where xn is less than b is equal to b. So suppose this is true. Now for any real number, for any real t, we're going to take b to be equal to the fractional part of negative t. Then, what does that mean? Well, what that mean is 1 over n, so n go from 1 to n of xn minus 1 over n by this uh, dagger equality is equal to, well, we'll take that to b minus 1 over n, the number of indices such that xn is less than b. And now take limit as big N goes to infinity. The right-hand side converges to 0 because this part right here, this part by our assumption converges to b, right? So the conclusion is therefore that the limit as n goes to infinity of 1 over big N of sum and go from 1 to big N of xn minus 1 over n sum and go from 1 to big N. This is equal to 0. Okay, so we got that. And conversely, Conversely, if the other way around is true, if for any real t, um, that the limit as n goes to infinity of 1 over big N is some, that the averages, the difference of the average of the translates equal to 0, then for any b between 0 and 1, what do we take? Oh, we just need to take a t where it's the negative t of that. So take any real t such that this is equal to b. In particular, of course, this means mm, yeah, it's not hard to come up with this, right? So we just need in particular, in particular, take t to be just negative b. That works, right? Because if t is equal to negative b, negative t is b, the fraction part of negative t is just b. Great. Then, by the fundamental equality, like so, the quantity that I'm looking for, the summation, sorry, the limit, no, sorry, 1 over big N of the number of terms such that xn is less than b is equal to, or minus b. Well, we can do, yeah, minus b is equal to 1 over n summation for translates with a negative sign here. So let me do that. This. And we know that this goes to 0. As n goes to infinity, therefore, the limit as big N goes to infinity, 1 over big N of this is b. There we go. So we have this fundamental lemma. The foundational lemma is basically saying that um, xn in bracket 0, 1 is equidistributed in bracket 0, 1 in parentheses if and only if and only if the limit as big N goes to infinity of 1 over big N of the number of indices such that xn less than b equals to b if and, for all b, be between 0 and 1, and if and only if for every real t, um, the limits of the difference of the averages so is equal to 0. So this is the foundational lemma that allows us to prove all of this, right? There we go. Pretty neat. In conclusion, we have Weil's theorem. Weil's equidistribution. It's probably discovered by someone else, but naming is never. Well, I don't know, right? But to my understanding, then therefore, for any irrational theta, comma, the sequence and theta is equidistributed in 0, 1. Here we go. All right, that's pretty cool. All right, great. Good, good, good. So what does that mean? That means if this is 0, this is 1, and you have some irrational number, theta, then 2 thetas here. Maybe you should consider the fractional part of it. Maybe this is 3 theta, and so on. It's just gonna fill this up dense, not just densely, but also in a uniform way. In a uniform way. Yeah. Now, of course, this also hinges on the fact that the sequence and theta, the fractional part and theta, is dense inside 0, 1, which we could also show. Okay, good.